In this exercise, we set up the integral for the outward flux of the vector function 6x squared y e to the x z through the surface of the solid bounded above by the paraboloid to z equals 20 minus x squared minus y squared, and bounded below by another paraboloid z equals x squared plus y squared plus 2. The two paraboloids seem to intersect along a circle. We should be able to use this curve of intersection to define precisely what the region of integration is. Let us call this region of integration capital D. We call the upper bounding surface capital S sub 1, and we name the lower bounding surface capital S sub 2. The outward flux through the upper boundary S sub 1 will be an upward flux. Hence, the integral for the outward flux through this boundary will be given by the following integral. It is the integral over capital S sub 1 of the vector field capital F dotted with a normal vector which is given by minus z sub x, which is the partial derivative of z with respect to x on the surface, and then minus z sub y, the partial derivative of z with respect to y on the surface, and the final component, which is positive 1, which indicates that we are looking at a vector that is pointing upwards. And since we are thinking of having z in terms of x and y, we are leaning towards integrating with respect to x and y. Based on how S2 is oriented, being a paraboloid that opens upwards, the outward flux through S2 will be a downward flux. The flux integral then on S2 is given by the integral over S2 of the vector field F dotted with the vector whose components are z sub x, z sub y, and minus 1. The third component being minus 1 tells us that this normal vector to the surface has a downward component. We will first work out the details for the integration through the upper surface capital S sub 1. First, we need to determine the partial derivatives of z with respect to x and y, and for this, we need to solve for z on the surface. Using the equation for capital S sub 1, we find that z is equal to 10 minus the fraction x squared plus y squared all over 2. It is now an easy exercise to find the partial derivatives of z with respect to x and y. Minus z sub x should be equal to x. Minus z sub y should be equal to y. And so the dot product of the vector field f and this normal vector is equal to 6x squared y times x, which gives us 6x cubed y, plus y times e to the x, plus z times 1. The only thing that we will do at the moment is to replace z by its formulation on the surface capital S sub 1. So we have the integral over the surface S sub 1 of 6x cubed y plus y e to the x power, and replacing z, we have plus 10 minus the fraction x squared plus y squared over 2. The only thing that we need to do is to write down the limits of integration. For this, we determine the inequalities that define the region D on the xy plane. We turn to the curve of intersection between S1 and S2. With the equation of S2 being x squared plus y squared plus 2 equals z, equating the z values between the two surfaces, we have 10 minus the fraction x squared plus y squared all over 2 equals x squared plus y squared plus 2. The viewer can easily check as an exercise that by moving all the variables to the right side, we get the equivalent equation 16 equals 3x squared plus 3y squared, or that 16 over 3 equals x squared plus y squared. This is the equation of a circle centered at the origin, and the radius is the square root of 16 over 3. Therefore, the y values start from the lower semicircle, where the y values are equal to minus the square root of 16 over 3 minus x squared, all the way up to the y values in the upper semicircle, where the y values are equal to the square root of 16 over 3 minus x squared. X then ranges from the value minus the square root of 16 over 3 on the x-axis to positive square root of 16 over 3. So now we can write down the flux integral for S1 with the limits of integration. Integrating with respect to y first and then with respect to x, the outer integral, which should be for integration with respect to x, should have the limits minus the square root of 16 over 3 to the square root of 16 over 3. The inner integral, which pertains to integration with respect to y, should go from minus the square root of 16 over 3 minus x squared all the way up to positive square root of 16 over 3 minus x squared. Then we have the integrand. So let us now take care of the downward flux through the surface S sub 2. Taking care of this normal vector to S sub 2, we use the equation of S sub 2 to determine the partial derivatives of z with respect to x and with respect to y. Z sub x is equal to 2x. Z sub y is equal to 2y. The dot product of F with a normal vector should be equal to 12x cubed y plus 2y times e to the x power and minus z. Replacing z by its formulation on S sub 2, the integrand becomes 12x cubed y plus 2y times e to the x power minus x squared minus y squared minus 2. The limits of integration should be the same as that for the flux integral for S sub 1, because S sub 2 also sits over the region D on the xy plane. Since the limits of integration for that of S1 and for that of S2 are the same, we can combine the two integrals by simply combining the two integrands. So for the outward flux, we have the same limits of integration. We combine these two terms, and we get 18x cubed y. Then we combine these two terms, and we get 3y times e to the x power. 10 minus 2 is equal to 8. Combining the terms with x squared and y squared, we get negative of the fraction 3x squared plus 3y squared all over 2. As an exercise, the viewer can check that the value of this integral is equal to 64 pi over 3.